Hello, this is topic number 2 for EET-250 Control System Theory. The title of this is Introduction to Embedded Control Technology. I'm going to shut my talking head off so it won't interfere with the presentation. So this introduction to embedded control technology, what we want to do is get an overview of what is known as embedded control technology. The goal of the module is to introduce the reader to this relatively old technology that is one of the enabling technologies of the next generation of Internet applications. That is, the Internet of Things, or IoT, or cyber-physical systems. Like many older technologies involving applications of electronics, the passage of time has served to make this technology much more powerful and certainly much less expensive. At the same time, other newly emerging technologies like wireless data transmission and the Internet itself have become pervasive. I wouldn't say that 25 years ago, but I would today. These additional enabling technologies have led to networked embedded controllers and more recently the promise of cyber-physical systems, which we haven't defined yet, but we will. Some theorize that in the future, with a great deal of networked embedded ambient intelligence, we will enter the era of smart everywhere. So this slide shows a slide from Horizon 2020. That's from the European Commission. And again, this program, Horizon 2020, ran from 2014 to 2020. So it's an older program, but the slide indicates the enabling technologies, those are the green arrows in the slide, that have been feeding the embedded technology field. Time is moving to the right in the slide. So on the far left of the slide, you see the start of embedded systems. Then what happens is network technologies came along, i.e. the Internet. Micro nano electronics became more sophisticated, and we started to have networked embedded systems. On the top you see the next green arrow is the Internet. On the bottom you see systems on a chip or smart systems. So again, the technology keeps moving along forward. Then on the top you see the Internet of Things, excuse me, cloud and big data. So again, these are products of the Internet of Things as we have evolved that technology. The bottom, you have a computing continuum, which kind of indicates that, computers everywhere. Within the green area, we see cyber-physical systems and smart everywhere. And again, we haven't defined what cyber-physical systems are. On the top, the last green arrow is user experience, human-machine interface. On the bottom, cognitive and learning technologies, which back in those days of 2014 to 2020, they didn't use the term artificial intelligence or machine learning. So there's a website link there for more information about that initiative. At this point in time, that might be, a stale website. It's hard to say. The program, however, has been succeeded by Horizon Europe, which again is the newer technology. So at this point, let's take a look at electronic devices, and we'll take a quick look at how the evolution of electronic devices has played out. Now, the vacuum tube, which was the original electronic device that can amplify electronic signals and can also act as an electronic switch, is approximately 125 years old. Really about 1906 actually started the first vacuum tube, but it wasn't until the middle of the next decade that actually they had vacuum pumps that were good enough to make vacuum tubes that lasted. The transistor, which for most electronics applications would obsolesce the vacuum tube, was invented about 80 years ago in December of 1947. So here's a picture of some vacuum tubes of 1914, and again, they look kind of like light bulbs, or some glass blower made them or something like that. And it turns out, again, one of the problems with getting early vacuum tubes to work was they really couldn't evacuate the inside of the glass very well until they got better vacuum pumps. On the right-hand side of this slide, we show the first point contact transistor, about 1948. And I always laugh. It looks like there's a paper clip or something connecting one of the components of this point contact transistor. Certainly, that wouldn't be a very good thing to build massive computers out of. They had to take and improve the architecture of that. So it took approximately 10 years to turn the transistor into a technical innovation. And this, when this finally happened, electronics changed forever. The solid-state era began. So the transistor proved to be a disruptive technology since it forever changed the rate of technological innovation in the electronics field. By the beginning of the 1960s, integrated circuits, or ICs, were ready to leave the lab. Now we enter the age of microelectronics. If the transistor was disruptive, the IC was even more so, and it heralded the start of the microelectronics era. ICs were ideal for use in the world of digital computers, where repetitive circuitry was commonplace, and the calculating proficiency or power of the computer was dependent on how much of this repetitive circuitry could be built into the machine and its relative cost. And again, ICs were perfect for this. This led to the introduction of the first microprocessor from Intel Corporation in 1971. There was actually 4 chips. The processor, the CPU, was called the 4004, and it operated on 4 binary bits at a time. So this slide is entitled Then. What you see here is a picture. This old printed circuit board, or PCB, from an early computer is representative of the technology of the mid-1950s to early 1960s. Known in the computer industry at the time as the second generation, that is transistor computer technology. The first generation obviously was vacuum tubes. This board, which is about 5 inches on a side, implemented or realized 1 byte, 8 bits of memory. The 8 pairs of discrete transistors, these are the round metallic devices, the silver round things in the middle of the board, and other components, the resistors and capacitors, provided 8 bits or a byte of storage or memory. Back in the day that these circuits were constructed, it turned out that to make what was called a flip-flop required 2 transistors or 2 active devices. So each pair of transistors on this is a single memory location, and there's 16 transistors or 8 memory locations, or what we call a byte of memory at this point. And of course, this slide's called In Now. So here's a ScanDisk USB flash drive, capacity of 1 trillion bytes of memory, and that's 1,024 billion times more than the PC board in the previous slide, and today costs less than $100, which would be much, much less than the PC board shown earlier. Back in the 1950s, that PC board probably was over $100 in 1950s money. And there's been, probably about a 10-time increase in inflation at that point in time. Now, here's another slide called Moore's Law. This depiction of Moore's Law, which is an observation, really shows how the total number of transistors on a microprocessor has increased over the past 6 decades. An affordable 1 terabyte flash drive came to the marketplace before the end of the last decade, in 2020s. See the previous slide. Its price will continue to fall with a 10 terabyte device now on the horizon. So Intel's slide here says aspiring to 1 trillion transistors in 2030, and it's got some check marks there: ribbon FET, power via high NI, which I'm not sure what that is, 2.5D and 3D packaging. So those are all techniques to put more transistors on an integrated circuit. And again, you see this line here, the straight line starts way back in 1970 and goes all the way to 2030. We're 4 years away from that. So what's the difference between a microprocessor and a microcontroller? It wasn't long after the introduction of the first 8-bit microprocessor, the Intel 8080 in 1974, that the semiconductor industry introduced the first 8-bit microcontrollers. So the question is, what is the difference between the two? Simply put, the microprocessor is a general-purpose computational device which needs other components to function. Those other components mean RAM memory, I/O, input-outputs, maybe a display, a printer, something like that, while the microcontroller can function on its own. And more detail will be provided later in this presentation. So again, the title of this slide, Microprocessor Microcontroller Operation. So before providing more details about the differences and similarities between these two types of devices, let's look at how information is represented by the physical hardware of these devices. If we understand this concept, it will be easier to understand how these devices function. Every computer represents information such as data or operational instructions as a certain length sequence of zeros and ones. So, the title of this slide is Information in the Binary Number System. In a microprocessor / microcontroller, zeros and ones are typically represented by a physical parameter like a voltage or current. In a kind of on or off scenario, for instance, 0 is a 1 and off is a 0. Or rather, on is a 1 and off is a 0. And that could be +5 is a 1 and 0 volts is a 0. Which the next bullet says 0 could be a lower negative voltage potential, while a 1 could be a higher positive voltage potential, or vice versa. Now, the binary number system, instead of our standard decimal number system, is used to represent mathematical values, as numbers, as well as other information. So the binary number system, like our decimal number system, is a positional notation system and obeys the same rules. However, its utility for use by electronic computing devices is that there are only two symbols, 0 and 1. And therefore, this fits the two possible states, on and off, of the particular physical parameter being used to represent the state, 0 or 1. The next several slides will provide examples of the binary number system. So the binary number system is the title of this slide, and what we call the base 2 number system uses two symbols, 0 and 1, whereas the decimal or base 10 number system has 10 symbols, 0, 1, 2, all the way up to 8 and 9. Notice that's 10 symbols for base 10. Base 2 has two symbols, 0 and 1. So using binary, or the base 2 numbering system, one can represent the numbers, say 23 or 107, in the base 10 or decimal system by the following 8 bits, or 1 byte of binary data. So you see 001, 0111, a base 2 representation is equal to 23, base 10 representation. Or the next example is 011, 1011, base 2 equals 107, base 10. Now, more basics of number systems. The decimal number system uses positional notation. And most of us learned this in elementary school, but we were most likely not aware of this type of terminology. The decimal or base 10 number system has 10 digits, 0 through 9, the largest digit being one less than the base. The decimal number system, the decimal number 564 consists of 5 100s, 6 10s, and 4 1s, or 564. Or we could represent it 564 in the following way: 5 times 10 squared plus 6 times 10 to the first power plus 4 times 10 to the 0 power. Now, if you take a look at that, 5 times 10 to the second power is 5 times 100, or 500. 6 times 10 to the first power is 6 times 10, or 60. And 4 times 10 to the 0 power, well, that you might question. Anything raised to the 0 power to make mathematics work is equal to 1. So that last term, 4 times 10 to the 0 power, is 4 times 1, or 4. You add those up, you get 564. Again, that's positional notation. In elementary school, you might remember the teacher telling you, oh, we're going to take and add up the ones column or the tens column or the hundreds column. So again, repeated here, this presentation is what is meant by positional notation. And the other thing you notice is that, say we added a number in front of the 5, like a 1 for 1,000. What would that be? That would be 1 times 10 raised to the third power. So you notice that to the left of the decimal point would be right after on the right of the 4, that we raise the base to first the 0, then the first, second, third power, and so forth. And that's said in the next bullet here. For a different number base, the same organization holds. So in the binary number base, the binary number system also uses positional notation. And of course, most likely you did not learn this in elementary school. So again, the binary base 2 number system has 2 digits, 0 and 1, with the largest digit being 1 less than the base. Binary number 10111 is equivalent to 16 plus 4 plus 2 plus 1, or 23. And down below I've broken that out. 1 times 2 raised to the 4th power plus 0 times 2 raised to the 3rd power plus 1 times 2 raised to the 2nd power plus 1 times 2 raised to the 1st power plus 1 times 2 raised to the 0 power. Or down below, 1 times 16 plus 0 times 8 plus 1 times 4 plus 1 times 2 plus 1 times 1, which equals 23. So that's how you can go from binary to decimal if you desire. Since the base 2 number system uses positional notation, like the common decimal system, there are rules that govern the fundamental math operations like addition, subtraction, multiplication, and division. Therefore, as it turns out, electronic circuitry can be built that will implement the needed steps to replicate these common math operations. This type of electronic circuitry is called logic circuitry. Today it's quite easy to build an electronic adder circuit that can add 2 binary numbers together. How about the representation of text? One might ask, how does a text editor like Microsoft Word store text files using binary? Well, through a selection of binary codes, any alphanumeric symbol can be encoded in terms of zeros and ones. There's something called ASCII code. ASCII code stands for American Standards Committee Interface Interchange. This code has been standardized for the representation of alphanumerics. Actually, computer keyboards automatically convert a key strike into an ASCII character for input. Each alphanumeric symbol can be encoded as a binary combination. And I think actually ASCII stands for American Standards Committee for Information Interchange Code. And it's probably like 60 years old, if not older. So ASCII code is the next title of the next slide. And we have some examples. For example, the lowercase letter A is represented in ASCII by the following binary combination. So if I was to tap the A key on my keyboard without the caps lock on or the shift key on, what would happen is the keyboard would present a byte of information of 011000001, 8 binary bits to stand for the lowercase a. On the other hand, if I hit the A with the shift key also, or the caps lock on, I would get a binary code of 01000001, 8 binary bits which represent capital A. The ASCII code is also used to encode punctuation and non-printable characters like the carriage return or escape or the $, for instance, all the functions / characters on a keyboard. So ASCII with the 8 binary bits could represent 256 different characters or functions on a keyboard. Keyboards do not have 256 characters. I think there are some Chinese keyboards that have 1,000, but the Chinese language is very interesting in its written form. What about hexadecimal code? Other codes are also used in the computer world. Hexadecimal coding is used as a shorthand notation to reduce confusion when communicating a long string of zeros and ones. So hexadecimal uses 16 symbols Those symbols represent 0 through 9 and A through F. For instance, for the previous ASCII examples, lowercase a, which is given by that binary combination for ASCII, is actually equal to 61 in hexadecimal. So if you take and go back to the ASCII coding, and there's 8 binary bits there, if you take the first 4 bits, you'd notice that that's binary 6, and the last 4 bits are binary 1, and 61. You go to capital A, and the ASCII code is shown there in the middle, and that's 4-1 hex. Well, if you take the first 4 bits of what's in parentheses, you'll have binary 4, and the last 4 bits are binary 1, or 4-1 hex. So some other examples here we might have here. 23 base 10 is given by that binary code in the middle, and that would be 1-7 in hex. Again, you break up what's in parentheses in the middle. The first 4 binary bits are 0, 0, 0, 1, which stands for 1 in binary. The next 4 bits are 0, 1, 1, 1, which stands for 7, and then it's 1-7 hex. 107 base 10 is given by the middle base 2 number, which turns out to be 6B in hex. So the reader may or may not be aware of the fact that the calculator comes with a Windows operating system, which I don't believe in Windows 11, is actually activated. You have to take and, I think, activate it as a mode available in the view mode called Programmer that can perform all these conversions, that is binary to decimal, decimal to binary, binary to hex, etc. You should give it a try, or the other thing is just to take and Google a online calculator, a binary online calculator. You'll find many examples of those, freely. Other representations of numbers. Other number representations are also possible, one of the most common being binary coded decimal, or what we call BCD. BCD has an 8-bit byte of information which represents 2 decimal characters. So here we have a number base 2 in parentheses on the left, 0, 1, 1, 1, 1, and 0, 0, 1, 1. And the first 4 equal to 7, and the last 4 equal to 3, or 7, 3 BCD. So the number 0, 1, 1, 1, 0, 0, 1, 1 in base 2 can be represented as 7, 3 in binary coded decimal. This type of coding was often used in early handheld calculators, digital multimeters, DMMs, and other electronic test equipment that used 7-segment displays because it helped out in the implementation of those. Now, this is a binary coded decimal to 7-segment display IC chip. On the right, you see a IC number to 7446, IC1, and you see a 7-segment display. The 7 segments A, B, C, D, E, F, G, and you see a bunch of resistors, R1 through R7, all 220 ohm resistors. Those are just, since this is a 7-segment display, has LEDs that light it up. It turns out that we need 220 ohm resistors to take and limit the current so those LEDs don't burn out. Or LCDs in this case, it looks like. So the diagram shows the circuits used by a typical LED display of an instrument before the advent of inexpensive LCD displays used today. The inputs of the 7446 IC, which are labeled A, B, C, and D, would receive a 4-bit binary coded value 0 through 9, and the internal logic circuitry of the IC would provide the correct combination of voltage levels on the A to G segment lines to light up the correct number. That is anywhere from 0 to 9. Other representations. So today for computer networking, Internet Protocol version 4, IP version 4, uses a shorthand notation for IP addresses that is a combination of binary octets given in dotted decimal form. For example, a typical home router might have the IP address of 192.168.1.1, or maybe you'd have a home router with an IP address of 10.0.0.6. That first IP address actually stands for or represents the binary value of, and here you see 32 binary bits. So the first 8 binary bits of this 32-bit binary number actually stand for 192. If you do the conversion from binary to decimal, actually the first one has a value of 128. The second one has a value of 64. 128 and 64 add up to 182, and the rest are 0 in that first 8 binary bits. You could do the same thing for the second 8 binary bits. It turns out to be 168. Then the last 2 groupings of 8 binary bits are both 1 and 1. So these IP addresses actually are 32 binary bits. So for IP version 4, the 32 bits are arranged as 4 binary octets, which are converted to decimal values, hence the term dotted decimal notation. IPv version 6, the successor of IPv version 4, and that's needed due to the exhaustion of IP version 4 addresses. You would think 32 bits would give you a lot, but not that many. It's 2 raised to the 32 power. It turns out the successor uses hexadecimal shorthand notation to represent the 128-bit IP version 6 addresses. And for the want of anything better as a descriptor, we call this semicolon hexadecimal notation. So the 128 bits are arranged as 8 groups of 4 hexadecimal values. 4 hexadecimal values yield 16 binary bits, which are separated by semicolons. So for example, this is a IP version 6 address, 3FFE, semicolon 1000, semicolon 5000, semicolon AFFA, semicolon 2000, semicolon 4000, semicolon FFFE, semicolon 12, well, I should say 12AA. And I'm getting caught up in the same thing that most people would do. We don't say 1,000, 5,000, 2,000, and 4,000, at least we shouldn't, because they're the decimal numbers. We're saying 1000, which is, again, 4 hexadecimal digits, which represents 16 binary bits. And that example there is a valid IP version 6 address. Don't get too overwhelmed by this. It turns out that only certain values of IP version 6 addresses are used, so it simplifies life a little bit. And we're hoping not to run out of these things. 2 raised to the 128th power is a lot of IP addresses that we will not run out of very soon. So, binary information summary. This concludes our discussion of codes by again stating that computers represent and store information as combinations of zeros and ones. Not hex codes or dotted decimal. We use those or these for our own convenience. You know, if I was to call you up on the phone and I said I've got a 32-bit binary address and I start rattling off zeros and ones, it would be very difficult for you. You would probably stop me and say, oh, please let me get a pencil and paper. Or if I said, okay, I've got 192.168.1.1, you could write that down real fast and convert it at your leisure afterwards. So hex is for shorthand notation. The computer knows whether binary combination is an instruction, a number, or an alphanumeric through various built-in hardware system cues or through the software program. For instance, consider that Microsoft Word uses the file extensions of .doc, .docx, etc. So if it sees something like that, it knows that it's a text file as opposed to binary numbers. A common thread during this discussion of information representation and the binary number system was that all our examples of descriptions of info used either 8 bits or multiple of 8 binary bits or a byte of information. Typically, the basic computer word is some multiple of 8 since the basic memory size is also 8 bits or a byte. An ASCII code fits in a memory location. IP version 4 addresses take up 4 memory locations. IP version 6 addresses take up 16, for instance. So let's now switch gears and take a look at the basics of microprocessor microcontroller operation. Now that we've seen how information can be represented in a microprocessor / microcontroller, let's look at the basics of their operation. Every micro has a basic set of instructions that can perform under program control. That's a list of operational steps. As mentioned previously, these instructions will use binary combinations or codes to represent them. These are called machine codes or opcodes. Every microprocessor, microcontroller would have an instruction set. So the Intel 8080 microprocessor, the predecessor of the venerable x86 family of Intel microprocessors, used 8-bit instruction codes. There are 256, 2 raised to the 8th power, possible combinations of 8 binary bits that could have been used to represent instructions for this device. But when it was built, only 78 were used by the Intel 8080. These instructions typically performed operations on other 8-bit binary words or data while implementing a program. Now, one of the things for instruction sets they called codes, mnemonic codes. So to make life easier for programmers, these 8-bit instruction codes had mnemonic codes which are easier to remember assigned to them. So typical mnemonic codes, this is basically for the Intel 8080, were add, and you can understand what that probably is, adding numbers, move, moving data, LDA, LDX, LDY. Those were load the accumulator, load the X register, load the Y register, stop, to stop a program, jump, to jump to a new location, halt, reset, decrement, increment, compare, IO, out, push, pop, etc. So, as an example, for the Intel 8080, the operation code or opcode for LDA, load the accumulator, was given by a binary value of 00111010 or 3A in hex notation. So if you were a programmer, you would probably memorize all 78 different opcodes or mnemonic codes and their hexadecimal notations. Going along with this, more mnemonic codes, the opcode for jump was given by binary 11000011 or C3 in hex. The opcode for halt was given by 01110110 in binary 76 hex. Of course, one can see that the 8080's opcode LDA by itself wasn't really very useful. It just specified the instruction, which was to load the accumulator. 2 more bytes of info, 16 more binary bits, were needed to designate the memory address of the data that was to be loaded into the accumulator. The Intel 8080 could address 16-bit memory addresses. This also goes for the jump instruction. It also needed 2 8-bit bytes to designate where to jump to for the next instruction. So again, note that 16 bits of data allowed the Intel 8080 to specify or address 64K, or exactly 65,536 memory locations, that is 2 raised to the 16th power, back in the day. Note that the 8-bit halt instruction needed no additional info since the instruction itself halted the processing of instructions. So back in the day, programming a micro was typically done what was known as machine and assembly language. One used the mnemonic codes and memory locations in hex to write the program, and then a program known as an assembler would convert the English-like machine code into zeros and ones to be loaded into the memory associated with a micro. Fortunately, this process has become a little easier today. We have things like an Arduino IDE, where we write C++ programming, and it turns out it does the automatic compiling and changing that coding to zeros and ones, which when you hit a button to take and download or upload the code to the Arduino, it does it automatically through the USB cable. So here's a microprocessor versus microcontroller block diagram. So earlier it was stated that the microcontroller was self-sufficient while the microprocessor was not. Let's examine that concept further by looking at this simplified diagram of a system based on a microprocessor. So you see the microprocessor on the left. There's a data bus. By the way, you might notice that some of the connections here are fat, black and fat, thick. That's a data bus, and the data bus has connections to memory, input, and output. Then there's an address bus. It is also fat, which indicates numerous bits, and it goes to memory, input, and output. And then the very output block, you notice that there are thin arrows, and it turns out that in the input and output, we discover we can take single bits into the input and output. So the nomenclature is that the big fat wires are multiple bits, or bus we call it, and the single wires are for single bits. So as shown by the diagram, to function as a system, the microprocessor needs other components like memory and input-output devices. And again, we said they're also shown in the data address buses and I/O lines. And these are used to connect the micro with other systems. So these electrical connections carry data in the form of binary combinations of zeros and ones, as mentioned before. The width of the buses, i.e. the number of wires, is typically a multiple of 8 for the data bus and address bus. Input and output can be single lines, as we've already mentioned. So here's a microprocessor motherboard. So this type of architecture, the microprocessor, gives rise to the classic motherboard for a typical desktop PC. The motherboard has sockets for memory cards and accessory boards that perform specialized functions. There are data and address buses that connect the micro to the components on the board, and peripherals like hard drives and DVDs for mass storage. There are I/O connections for a keyboard, a mouse, VGA, USB, audio, video, and so forth. So this is a gigabyte board, and you might see the processor looks like it's kind of in the middle right of the picture. Looks like memory boards go in the upper left-hand corner. You might see in the very top right you have I/O or communication interfaces and so on. Now we have microcontroller, and it turns out the microcontroller looks just like the microprocessor we had before, except it's on a single chip. So on the other hand, the microcontroller is fairly self-contained, shown by the simplified diagram. The data bus and address bus and memory and I/O are on board the IC chip. Notice that the input and output go to the off the chip. So here's a typical industrial microcontroller board, maybe a little bit dated because I see it looks like it has an RS-232 connection in the top right there, but also looks like it has an internet connection and a power connection. So this small, roughly 4 by 5 inch PCB is a typical ARM microcontroller board, and ARM stands for a certain type of architecture. Comes with several standard computer serial I/O and USB port connectors, analog signal input headers, an external SATA hard drive headers, and a standard gigabyte Ethernet networking connector. The only thing lacking on the board is the power electronics needed to supply the required power to run industrial equipment. So the next couple slides are going to be a teaching tool. Now, the Intel 8080 was introduced roughly 50 years ago, so it is not something we use today. However, it is simple enough, but also representative of how microprocessors operate. So I'm going to use it as a teaching tool. Again, we've gone way by this, but this will give you an idea how stuff works. So if you take a look at the diagram, what you see is the CPU, or central processing unit. The big red ALU, arithmetic logic unit, is kind of the heart of that. Over to the right there is a bunch of registers, W and Z, temporary registers they're called. The B register, C register, D register, E register, H and L registers, a stack pointer, program counter, an incrementer, decrementer, address latch, an address buffer, and that leads down to the bottom right-hand corner of A0 through A15 address bus, or 16 binary bits. Up top, there's a data bus, D0 through D7, a bidirectional data bus, which means it turns out that 8 binary bits come in, and there's a data bus buffer and latch. Those bits come in, they go to an instruction register. There's an instruction decoder and machine cycle encoding. Then there's all the buses where things can move around in here. You notice in the top left-hand side of this, you got an accumulator, an accumulator latch, a temporary register. There are things called flag flip-flops. The arithmetic logic unit, the red device there, gets information from a temporary register and from the accumulator latch. There's a decimal adjust, and down below, timing and control. There's a write, data bus control, interrupt control, hold control, wait control, sync, and clocks. And there's a reset. So it turns out that there was a very complicated thing, but at least you can understand basically what's in here. So on the right hand side, figure shows a block diagram of the original Intel 8080 microprocessor. Internally, it consisted of an arithmetic logic unit, the ALU, various registers, which are flexible memory cells, an instruction decoder, a timing and control unit, and data pathways between these units. So the next few slides will give you an idea how this device worked. So the top of this slide says fetch, decode, operate, and store, 8 bits at a time. So the diagram on the right, consider what happens. Consider the basic operation of microprocessor architecture shown here. The initial operation upon powering up is to fetch an 8-bit binary word from the system's external memory using a specific 16-bit binary address. By default, this initially fetched word is decoded as an instruction. So we reset this device, it goes to a particular address, and it gets an 8-bit binary combination which it believes is an instruction. It's brought in through the bidirectional data bus, goes into the instruction register, and gets decoded. So we already talked about the first bullet here. The 8-bit word is interpreted and decoded by the logic in the instruction decoder. At this point, the decoded operation begins to be sequenced to its completion by the timing and control unit. Next, the specific operations performed using the various registers, which again are flexible memory locations wherein contents may be modified, and the ALU, the arithmetic logic unit of the CPU. Note that data may or may not be needed to be accessed from memory or other registers to perform the particular decoded operation. Finally, the results of the completed operation is either stored internally in a CPU register or out in an external memory location via the data bus latch. At this point, the 16-bit program counter, that's called the PC, on the right hand and the kind of light red or pinkish unit over on the right hand side of the picture, that points to a memory address, and it is incremented so as to point to the next program instruction in external memory. So again, remember, we turn this thing on, we reset it, it goes to that particular location, grabs information, brings it in, interprets it as an instruction, does whatever that instruction is, which might bring more stuff in from memory. Then it goes and increments the program counter to look for the next instruction. Non-branching programs execute in this fashion. It is very possible that depending upon the results of a particular operation, the working program will call for a branch or jump to an instruction other than the next one in sequence, i.e. that's branching to a subroutine, it's called. When this happens, the PC value must be modified accordingly, and the CPU stack pointer, or SP, will keep track of the old PC value to allow for an orderly return from the subroutine. So again, if we have a jump command, it turns out we will alter the contents probably radically of the program counter to go to the subroutine. Implement that subroutine, and when we're done with it, we'll go back to where we were in the program. We'll return using the stack pointer contents. So most computer application programs consist of instructions and subroutines and run in a constant loop to control some operation. The programs are looking for inputs, which we call interrupts, or are constantly looking at sensor data to evaluate and alter the flow of the program. For instance, electronic fuel injection, if necessary. A PowerPoint program is waiting for a key strike. For me to take and advance a slide on a PowerPoint presentation, I have to do a key strike, And it turns out that provides an interrupt which moves to the next slide. Consider how we could multiply two numbers with this old technology. We could multiply 8 times 9 by adding 8 to itself 9 times. We would load 9 into a register, and every time we added 8 to itself, we would decrement the value stored in the register. When the register value became 0, we would have our answer and stop the process. Now, some other comments. Clock speed. Typically, we talk about the processor's clock speed. Gives us an idea how powerful it is or how fast it is. The lowly Intel 8080 had a clock speed of 2 megahertz or 2 million pulses per second. What this means is that instructions typically took 4, 5, 7, 10, or 11 cycles of the clock to complete. Therefore, the Intel 8080 could process a few 100,000 instructions per second. Today, our clock speeds are up in the gigahertz region. More hardware details. How do these CPU components, registers, decoders, ALU, flag flip-flops, multiplexers, and so forth work? They use electronic circuitry known as digital logic gates or combination of these circuits to perform their functions. These logic circuits take in binary input signals, zeros and ones, and produce binary outputs, zeros and ones, based on a desired set of Boolean algebra-based rules. What this last statement means is that for a certain combination of inputs, the various outputs will be ones or higher active. For the other possible combination of inputs, the outputs be zeros or low or inactive. Typically, we display the circuit's operation with a truth table. For instance, the ALU might add two 8-bit binary numbers together. The least significant bits, the LBSs they are, the rightmost bits are added first. The LSB circuitry of the ALU takes in two binary bits and produces the following outputs. An output of 0 for inputs of 0 and 0, an output of 1 for an input of 0, 1, or 1 and 0, and lastly an output of 0 for an input of 1 and 1. These are the rules of binary addition. For the last case, an additional carry bit, a binary 1, will be sent to the next significant bit position circuitry to account for the math operation overflow. This action is required for positional notational number systems. You know that from knowing how to add numbers. The next significant bit and all other bits of the ALU now deal with 3 binary input bits at a time. The 2 bits from the binary numbers being added and any carry bits from the lower bit position. In other words, the ALU performs a binary addition function on 2 binary words. Finally, if the 2 binary numbers being added overflow the ALU, a flag or carry bit is set in the flag register to indicate this fact, which most likely needs to be acted on. Refer back to slide number 44 to see the 8080 flag register. So here's an 8-bit ALU adder example. This figure depicts the operation of the addition of 2 8-bit binary numbers by an 8-bit ALU. Register X contains the number 215 in binary, and register Y contains the number 181 in binary. The results is the number 396 in binary. That's a 9-bit binary number, or 256 is the carryout value, plus 140 in the 8-bit ALU register. You add those together, you get 396. More hardware details of logic. There are basic logic gates like AND, OR, NOT, NAND, NOR, inverter, etc. that perform the basic Boolean logic functions. For example, the AND gate output is a 1 only when all inputs are 1, while the OR gate output is a 1 whenever any input is a 1. Other complex functions like registers, an ALU, instruction decoders, multiplexers, etc. are made from combinational logic, that is, combinations of logic gates. Today we have field programmable logic arrays, FPLAs, or gate array technology. These devices consist of vast arrays of these fundamental logic gates or blocks on an IC chip. These logic blocks can be programmed to interconnect with one another to provide a multitude of complex logic functions, from the simplest logic functions to processor cores, i.e. generic microprocessors. The first practical CPU, 8080, was quite crude compared to today's processors, but it was the start of a revolution in technology. Today, we have 32 and 64-bit operating systems, OSs. This means that data is manipulated 32 or 64 bits at a time within the CPU. Note, however, that data is still stored in 8-bit or byte memory locations. Therefore, instructions might point to a single precision data word that is stored in a 4 or 8-bit location, i.e. 32 or 64 bits. We also use floating point arithmetic, which allows us to perform complex mathematical operations with great accuracy on data words with more than single precision. Since our goal is to give an overview of the embedded control technology, we will leave the details of newer computer CPU technology